Okay, so I'm going to talk a bit about psychology for a bit, and then get back into economics, hopefully. So hopefully this has some echoes with some of the talks we had before, specifically about how people don't really know about the probabilities that they're trying to deal with. So the starting point for this is that there's been lots of work for a long time in psychology showing that people don't reason well with probabilities, and probably they don't know probabilities themselves at all. And so John gave some great examples of this, where you just wouldn't be able to guess what the probability is that Harrisburg is the capital of Pennsylvania, which is something I should have known being educated in America. But instead, what people might be doing is using samples instead of probabilities. So instead of actually knowing the probability that anything is true, what you do is you just try to think of some examples of it being true, or some examples of it being false. And then you kind of build up examples over time, and that eventually will give you something like a probability. So you don't actually know the probability that something is true, you kind of have to calculate it over time using examples. And examples are a nice way to think of how human cognition works, because we experience examples in the world. It's easy to produce examples, like I'm producing examples of language and so on. So it seems like kind of a natural way that cognition can work. And of course, if you produce samples, you don't actually have to know anything about the probabilities themselves. So you can use devices like this Galton board right here to produce a normal distribution. That doesn't require knowledge of the probabilities of the normal distribution. It just kind of generates them from these simple interactions of how these balls fall. So if people really are using examples in order to do reasoning, a big question is, how do they generate these examples in the first place? So one sort of simple hypothesis is that they just generate them according to their probabilities, identically distributed and independent. And so something like a Galton board would do this, right? And this can explain a variety of different kinds of biases you see, some of those ones that are introduced by Kahneman and Tversky. So that was one hypothesis. Another is that instead of being able to generate these examples, just according to probabilities, which actually would require a lot of knowledge about the probability distribution, instead what maybe you do is sort of like randomly walk around this probability distribution. A random walk that's kind of biased toward higher probability hypotheses. And if you do that, you kind of have a sense of location, which is something that you feel happens in human cognition. So if I come up with a hypothesis for, explaining a certain phenomenon in the world, the next hypothesis I come up with is probably going to be similar to that. It's not just going to be another randomly generated one that's far away from it. You kind of have this sense of, the things that you think of are similar to the things that you thought of before. So if you think of a random walk around the space of hypotheses, you do it a lot, and if you trace your path back and look at all the examples you've produced, you end up with samples from this probability distribution if you do it in the right way. So that's another thing that can explain a lot of other kinds of effects that you might see that you can call reasoning biases. But if you're dealing with a really complicated sort of probability distribution, and you don't know enough about it in order to directly draw samples, you might want to do something a little more complicated. So this is an algorithm that they came up with in statistics to deal with the problem of multimodality. So maybe there's a lot of different hypotheses that can explain a phenomenon that you see, but these hypotheses tend to be far away from one another. They're not all sort of clustered and sort of small deviations from one another. And in that case, something like this random walk model is not going to do very well. It's not going to be able to transition from one mode to another mode. So you might want to do something like this metropolis coupled MCMC, which runs a bunch of chains, some of which kind of sample from the right distribution, and other which kind of explore the space better by sampling from a distribution that's raised to a temperature. So basically it's like a flatter landscape. And every once in a while you kind of switch between these states, which allows you to make these big jumps. And then the rest of the time you make sort of these small innovations. So you think of things that are similar and occasionally make some big jumps. So these are just some examples of algorithms from statistics that we could use as candidates for how people think of things. So how can we actually identify what's going on? So one way to do it is to ask people to generate a long series of answers. So we started to do experiments like asking people to think of all the animals they can think of. And every time they think of a new animal, they just sort of write it down. So you can see like how they transition around the space of animals. And another kind of terrible experiment, terrible for the subjects, but really good for us, is we asked them to estimate how long a second was. So they would hit a key every time they thought a second elapsed, and they would do this 1,000 times. And that takes about an hour. And what you see... Yeah, £6. It's incredible. Yeah. So what you see is you can get basically a time series of the estimates they make, every time they hit this button, how long elapsed actually between the times they said were 1 second apart. And if you look at something like this time series, you can see lots of sort of interesting effects that occur not just in this task, but also other tasks, like this animal generation task. So So one of these effects that you can see are that most of the time people make small changes to their estimate, but every once in a while they'll make a big change. So here they go from about 600 milliseconds to 800 milliseconds, a big change. And then they kind of stick with that for a while and then they switch back. So if you look at the distribution of the changes that they make, it looks like this Levy distribution with lots of small changes with occasional big changes. They have this heavy-tailed change distribution. And another thing you can find is that if you look at the autocorrelations of people's changes, it's not independent, right? They're not just drawing samples independently from what they think a second is. So it's not something like white noise. It's not based on the last estimate that they made. It's not like a random walk itself. Instead, if you look at the autocorrelations, they look like 1 over F noise, which is sort of the estimate that you make depends not just on the previous estimate, but like every estimate you made before, which is a very sort of strange thing. So if we look at these algorithms again and see whether they can explain these kind of time series we can see in human cognition, something like direct sampling can certainly work well in multimodal distributions, but it's really, really hard to do. You have to know a lot about the distribution in the first place. It doesn't really make a lot of sense. And also the sort of statistics it produces, it generates independent samples, so that doesn't really describe what people do. Something like a random walk is like a pretty good candidate, and that has these dependencies. The dependencies are not of the right type. They only depend on the previous state you're in, basically. And the jump sizes you get tend to be Gaussian if you use the right sort of distribution. So something like this algorithm I was talking about that can deal with these multimodal spaces without knowing much about them. This can both produce these sort of Levy flights that you see, these big jumps occasionally, and also these long-range sequential dependencies that occur because you're trying to explore this space that's very hard to get around. All right, so this is sort of work that we've just been producing in psychology, and we quite boldly decided to just try to apply it to financial markets and see what sort of things we could see and whether there's any similarities here. So we took as a starting point this review from Kant, who talked about these stylized facts about speculative prices. So we came up with these sort of 11 stylized facts that you can see in asset markets. And we focused on 4 of them that we thought were sort of paired well together. So one of them is that there's an absence of autocorrelations in asset returns, so you can't really say if something goes up whether it's going to go up again. But you see volatility clustering. So if you are in a period of high volatility, then you're going to continue to be in a period of high volatility, most likely. You also see on short-term returns, heavy tails, so you can see big jumps and a lot of small changes as well. It's like a power law. But if you look at a longer range, you see something that looks more Gaussian. So you see the returns kind of look more like a normal distribution. So we first tried to think about whether these price movements could be explained purely as mental fluctuations. Like maybe people are sort of sampling from a distribution of what they think the future price will be. So we started with a really simple case where we assumed that people were just drawing samples from a normal distribution. And every sample they drew was going to be a sample from this normal distribution. We wanted to see what a time series would look like. Whether these algorithms could produce the same sort of time series you see for financial markets. So we have our 3 different samplers here, the direct sampling, the random walk, and this MC cubed algorithm. And we just say that the price is basically people's belief, though we'll try to get a little more complicated after this. So if you do direct sampling, then basically you just see a whole bunch of independent samples right here. So this is your price, which is just samples from this normal distribution. And if you look at the returns, basically the difference between one and the next, you get another set of independent samples from a normal distribution. And it doesn't matter how long you aggregate over, whether it's just one time period or you look at 1,000 time periods, you still get this Gaussian distribution. The asset returns are uncorrelated, which is good, but also volatility is uncorrelated because everything's independent. So this doesn't explain what's going on. So it kind of gets the kind of easy things, like the absence of autocorrelation in returns and the Gaussianity, but not the other stuff. We can look at a random walk. This is a random walk metropolis, which is very similar to like a normal random walk. And we kind of see this normal random walk behavior, but the changes you see between each time step and the next are just Gaussian, drawn from a Gaussian distribution, basically. So they are independent, and so you get independence in asset returns, but also independence in volatility. And the kind of distributions of returns, both on the short and the long scale, tend to be more Gaussian. And then finally, we can try our last hypothesis about how human cognition works. Maybe there's something like this MC cubed algorithm. And so you can look at the time series it will generate, and it tends to have something that looks a bit different. And if you look at the returns, you can see sort of these bursts of changes, while occasionally there's other times where it's very quiet. And the returns themselves are very interesting. They don't really exhibit much autocorrelation. That sort of drops out very quickly. But the volatility itself does have long-range autocorrelations. So you know that it's going to change a lot, but you don't know what direction it's going to go. And basically, the returns themselves look a bit heavy-tailed on short terms, but since it's sampling from a Gaussian distribution in the first place, in the long run, it's going to draw samples from a Gaussian distribution that's going to look like a Gaussian distribution. So this one at least can explain some of these facts that are some of these stylized facts about asset markets. And then we thought we would try to make it a bit more realistic. So instead of just thinking about the prices that occur in markets purely as imagined prices, we tried to use this classic DeLong et al. Model about how noise traders would act in the market. So we said that, as they did, that the noise traders are basically drawing a sample from some sort of distribution, and this is the error that they make about the true prices. And we have a bunch of market mechanisms, which is the market mechanisms that they assumed. It's an overlapping generations model. You have some percentage of noise traders, some percentage of rational traders, and they all sort of determine how much they want to split this risky asset, or they can put as much money as they want into a risk-free asset. And based on these market mechanisms, you can come up with a pricing function, assuming that the market's clear and that it has a steady state, which is probably not quite accurate. And what's interesting about this model, this pricing function, is that everything is a constant except for this random variable, which is the sample from the distribution. So essentially, if we take this particular model seriously, then we could think of these imaginations that people have as like the only random thing. And the pricing function is essentially a linear function of these imagined prices that you have. So basically, that's a linear function of this time series that I've shown you before, and it still has all these statistical properties, where the asset returns have almost no autocorrelation, the volatility has a long-range autocorrelation, and you see something moving from a heavy-tailed distribution to something light-tailed as you get a longer time period. So that's it. We have this sort of sampling approach that we think is useful for human cognition. I can sort of explain the sort of time series that we see. We've been trying to see whether we can combine it with existing financial theories to sort of explain some of these stylized facts about asset markets. And this is really preliminary. I'll certainly acknowledge that and thank the funder. And so there's a lot more to explore.